Hi, linear algebra students. This is the third and last video on topic 1.4, so the matrix vector product. Okay? First, let's have a look at the theorem. If A is a m by n matrix, okay, first of all, I should remind you once again that m is the number of rows and n is the number of columns. Why is this important? It's because the u and the v, the two vectors that I'm talking about, must be in Rn. In other words, they must have as many components of, as many components as A has columns. And this is very important. Remember that otherwise the matrix vector product is undefined. And C is a real number, so a scalar. Then in this case, the matrix vector product satisfies these two properties. So A times a sum of vectors, u plus v, you can do A times u plus A times v, okay? In other words, we say that the matrix vector product is distributive. Yeah, that's it. It's distributive. We could be more precise and say left distributive, but distributive is nice enough as long as we know what we're talking about. And the second property, notice that it means it's associative with a scalar, or it commutes with, it commutes with scalar multiplication. There you go. And the point of this video is to do the proof of these two statements. And we will do the proof only in the special case, the one in which n is equal to 3. And the reason for that is because if we are able to do the proof for n equals 3, it's easy to generalize to higher values of n. Okay? So let's start with 1. So if n is equal to 3, we have A times u plus v, like this. That is equal something like this. A1, A2, A3. And then the vector u plus v, we know how to add it, right? The first component will be u1 plus v1. The second component will be u2 plus v2. And finally, the third component will be u3 plus v3. Now, remember, we will use here the definition of matrix vector product. So this will be A1 with u1 plus v1. I prefer using the usual color code. So in this case, green. So A1 will be with u1 plus v1. Then A2 goes with u2 plus v2. And finally, A3 with u3 plus v3. So in other words, the matrix vector multiplication is going to be the linear combination using the weights. So u1 plus v1 multiplied by the vector a1 plus u2 plus v2 times the vector a2 plus u3 plus v3 times the vector a3. All right. At this point, these are numbers, right? The u1, v1, u2, v2, u3, v3, these are all real numbers. And it means that with a vector like this, it's going to be right distributive. So we can say that this is u1, a1 plus v1, a1. And then we do the same with all the other ones. So u2, a2 plus v2, a2. And finally, plus U3A3 plus V3A3. All right, now the next step is very, very important. These are all vectors, and we have seen that vector addition is commutative, which means that we can change the order of all of these terms. And the strategy is to go U1, A1, then you put it with U2, A2, U2, A2, and then with U3, A3. Plus, and then you pick up the terms that go with the V's, right? V1, A1, plus V2, A2, plus V3, A3. Now, here's the big idea, okay? Right here, you end up having, by definition, A times U. And also here, you're having, by definition, A times V. So in other words, you proved that this is AU plus AV. So this is the proof of 1. So we proved this part right here. Let's erase this, and we're going to proceed proving the second part. The idea is exactly the same. So we know that A is going to be written as a matrix with A1, A2, and A3. But then we also know that the components of U are going to be C1, green, C1, CU1, sorry, there you go. Then we're going to have the second component CU2, and the third component CU3. At this point, we're using the definition of the matrix vector product. So it's going to be the linear combination of the columns of A with the corresponding weight. So CU1 times A1 plus CU2 times A2 plus CU3 times A3. Okay, from there, we are going to use associativity, okay? So in other words, we're going to turn each one into C times U1, A1. Okay, so we're going to turn the green into that, and we're going to do obviously the same for the other two. So it's going to be C times U2, A2, and then finally plus C times U3, A3. Now this is where it becomes really important. So as you can see, this number C right here is actually a common factor, meaning you can take it out. So it's going to be C multiplied by, in big brackets, these three things. So what's left in each of them, I mean. So U1A1, U2A2, and U3A3. Like this. And here, your proof is done because what you have here turns out to be the product A times U. Okay? So in other words, what you get in the end is the right-hand side of this equation. So C multiplied by AU. And this is the proof of 2. All right, this was the third and last video on the section 1.4. So I'm just going to repeat the outcome. I'm not going to present this in class. I'm going to go straight to 1.5. However, you don't have to submit this in the second week's. You don't have to submit this as this week's lecture notes, but of next week's lecture notes, along with your assignment number 3. I'm going to explain this a little bit clearer, actually. So yeah, forget about that last point, but I'm going to write a message telling you exactly what I'm expecting. Have a great one. Hopefully this helps.